And actually, it has to be something we can interact with. Okay, but right now, let's get Cesare going. Cesare is one of the important reasons we're here. He's developed many of the ideas that go into proof automation. He's also done a lot of serious legwork in making sure that SMT solvers have a uniform interface, and it's a very kind of rich ecosystem that he's designed and developed that many groups benefit from.
That's an introduction. So you have 20 minutes or half hour?
Half an hour. Yeah.
Okay. So I'll tell you today about our attempts. Well,
maybe take
so permitting.
So you put on the table so it's not pulling on the console.
Cable is not full.
No, but I think you just mean something like
Yeah,
this.
put it on
yeah,
there.
like that,
Yeah.
so that there's not constant tension.
Right.
Yeah. Green stretch tape?
So I'll tell you today about our attempts to capitalize on the power of some of these automated reasoners to increase the automation and improve assistance. In particular, we focus on Coq. This is joint work with a bunch of people in my group and in Clark Barrett's group. We developed CDC4 together. And Burak Ekici and Alain Mebsout are the ones who did most of the work I'm going to tell you about today. And this is based on earlier work by a bunch of people, at least one of whom is here, that developed the first iteration of a plugin to integrate a set of SMT solvers into Coq. And the common person here is Chantal Keller, who is the main developer of such a system. So again, what's the main goal? Increase the automation in Coq specifically. And we want to do this by bringing the power of SMT solvers into the system while at the same time maintaining a high level of trustworthiness. And as a side effect of doing this, we also, because of the way we're going to do it, we also get an independent checker for proofs produced by SMT solvers that can be incorporated into Coq. Although that's not going to be the focus of what I talk about today. Automation is the main focus. So a realization of this goal was the SMTCoq plugin that again was developed by Chantal and her collaborators a while back, that you could understand as having essentially these functionalities. It's a converter from Coq goals to SMT formulas, then a certifying checker that gets sends the goal, after sending the goal to an SMT solver, gets a proof participant back and checks it internally in Coq. And a set of tactics to put all of this together. So the idea here is that, the idea that motivates this work is that along these three dimensions, we have a system like Coq, or proof assistants in general, that are very expressive. We have very high confidence of their correctness, so they're very trustworthy because of the way they've been developed, but don't have a lot of automation. In contrast, you have some T solvers such as ZC4 that are fairly expressive, very highly automated, and well, provide some level of soundness, but not too high. They're not too trustworthy. Not because their algorithms are unsound, but because they are complex in terms of implementations, and so they typically contain bugs. So what we would like to do is, in a sense, combine the two and get the best of both worlds, if we can. Now on the Coq side, the idea would be, and this combination is going to be done through the SMTCoq plugin, to increase the level of automation while maintaining the same performance on the other levels, expressiveness, soundness. And well, as I said, as a side effect, you would have also that. But once you have this infrastructure in place, you can also increase trustworthiness independently of SMT solvers, because to be able to incorporate it into a system like Coq through SMTCoq, they have to be proof producing, and then you can check their proof independently. All right, so again, what is this? What is the main idea of SMTCoq? To get a bit more details. So SMTCoq has been developed with this sort of workflow in mind, that at some point the user is using a goal that falls into the fragment that could be addressed by an SMT solver. I'll be more precise later. Then it sends this goal to an SMT solver through a tactic, but not to any SMT solver, but to one that is proof producing. Once it's able to prove a goal, it also sends back a proof certificate. So you get the proof certificate, you check it internally using a verified checker, and as a consequence, by reflection, you get a theorem back in call. This is the theorem corresponding to the original goal. So this allows you basically to dispatch some goals to an external solver without sacrificing samples. And this will be the main method. So the idea is quite simple. Of course, the tricky part is to make this work in a way that is, one, correct, and two, relatively efficient, so that a user, a typical Coq user, will benefit from this. So how would that work? Again, yes.
Just
Interrupt me anytime, by the way.
just a quick question about the way in which current SMT solvers may not be sent. Does it manifest itself in the current implementation in not being able to find the certificate, or in the certificate itself being incorrect, usually?
So, well, I'm going to tell you about this right now, but the idea is basically you get a certificate back and you need to check it, and if the check doesn't succeed, then you won't trust the result of the solver. Now, there are other reasons, of course, the proof might fail. It might be that, well, first of all, the goal is invalid to start with, right? It's just not a theorem. Or you might have, some kind of runtime error externally in the solver. Or the conversion might fail. Or internally, the certified checker that is supposed to get back the proof from the SMT solver and check it takes too long. Right? I mean, there are many ways where this can fail, but in terms of what I think you had in mind, the failure is effectively what I can't check. All right, so how would that work? The goal is, well, essentially translated into an SMT formula through a verification process, because we have a deep embedding of SMT formulas into Coq for correctness purposes. It's sent to the solver. The solver, if successful, produces a proof witness. This proof witness is pre-processed in a number of ways, and in particular, it's converted from the format used by the SMT solver to the format used by SMTCoq. The certificate is checked, and this, together with the already proven soundness of the checker, gives you the ability to claim that the goal indeed is true. Well, one case is that the goal you started with is invalid, and in this case, we would like to be able to tell the user, well, look, the goal is invalid in the first place. So we have added mechanisms to be able to do that. I think this is the first in Coq where you actually told, this is not, the proof doesn't go through simply because the goal is invalid. And here's a counterexample of that.
Yeah, but this is modulo the axioms that you receive at the CVC4 end of things, right?
This is always modulo the theory that you're working with.
Yeah, but
right?
what I mean is in Coq you have a theory with thousands of lemmas, and probably you don't export all thousands. It's just the user says, try to find a proof with this and that and that. So the model is just relative to that, and therefore it just tells you need more lemmas.
Yeah, well, it simply means if you're sending a goal that you're trying to prove, it simply means that in the theory supported by the solver,
Right.
the goal doesn't hold.
Right.
And so perhaps you need to send, a bigger goal,
Right.
a conditional one.
Just quick question, does that happen often? Because you have a theory of quantifiers, I guess, or you're not using it in that bridge?
We're not, at the moment, the fragment that we use is effectively quantifier-free. So this happens.
Because in Isabel we had these potential counterexamples coming back, and they were more confusing to the users than helping, so we got rid
It's
of them.
possible, we'll see this in the
Okay.
demo a little bit. See that. that helps in the demo. Okay, so,
Got a question around the
Yes.
previous slide. There didn't seem to be anything trusted on that slide.
I'm going to tell you in a moment. The next slide. Right here. So these are more details about the architecture of the system. Okay, so again, once you have translated the goal to an SMT formula in the SMT2 format specifically, and you give it to the SMT solver, you get a proof witness. I said that's preprocessed. But in fact, what you also want is to read the formula back into the system, because you don't want to just check that you got a proof of something. You want to check that you got a proof of the formula you started with. Okay? So that means you also have this SMT-lib parser. Now this is the only trusted component of this whole system. Okay? It's a relatively simple parser. You know, the SMT-lib format is fairly simple. So you could trust it, or convince yourself that it is correct. The checker, of course, is certified, so we're good. The solver and the preprocessor are untrusted, but they are completely out of your trusted core. You don't need to trust anything about them. Yes.
I don't really understand why you have to state that the parser is also trusted. Maybe we will discuss that later.
Well, I think if there are two aspects to it, right? There's the aspect of invoking SMT4 from CoQ, where it doesn't matter, but there's also the aspect of reinforcing the trust story of CVC4, and then you trust it, right?
But see, the problem here is that, again, you got a proof back, and you need to know that this is the proof of your goal, right? So you need to be able to relate your goal to the formula that was generated.
Where does the input
Right.
come from? Where does the input comes from? Where does this input comes from? Is it like in file,
In a file. Yeah.
Yeah, but
So
if
you're
you have
reading-
interface to the CoQ itself, probably you can have some.
Say this again, sorry.
If you have interface to CoQ itself, yes, then you can avoid file.
Yeah, I mean, this could be done in a way where we eliminate this, okay? In principle, we make it even smaller, but for the moment, this is the current situation.
Okay.
But
So you need
when
to
we
trust
do,
that the parser is correct.
but wait a second, so I just want to really understand this. So if the parser is incorrect, can you prove something in CoQ that, can you prove false in CoQ? And I think the answer is no.
No.
Right, so then it's not
So
trusted from a
we don't need to trust the parser.
Right.
But if you want to
No, I
consider
mean,
it the thing
I
that's
think
proved
you
to
could
answer
be
your original
proving-
question.
I think
Right, but
you're looking at it in the
that's
context
from
of.
the CVC4 point of view, that's what I was trying to
But
say.
you trust the cook parser in this case. So maybe
Right.
it's worse.
No, but I think this is independent of the
we get back to
client context.
This is from the CVC4 point
Yeah,
of view
yeah.
and the
Yeah.
trust story of CVC4.
Yeah.
Right, that's what I was trying to clarify with my previous question. It was
I
probably
think
not
we'll
clear.
have time to discuss.
Okay, let's discuss this offline. But the important point, however, so let's simply ignore this for a moment, is that neither the solver nor the preprocessor have to be trusted, because if there's a problem in there, then the proof will not go through. Now, how is the actual certified checker developed? And this is some work that was already present in the original SMTCoq. As a reminder, what we did was to improve on it and extend it. It's designed to be highly modular, so it's composed of a number of small checkers, so to speak, that specialize on particular theories or fragments of these theories, or even aspects of deductions in these theories. For instance, there is a small checker for CNF conversions from standard formulas to clauses. Usually SMT solvers use CNF internally. There is a small checker for resolution proofs. Most SMT solver proofs have a basic structure, which is a resolution proof, and then this resolution proof also uses lemmas that are valid in the theories, and so they're accompanied with their own proofs. Then proofs of these lemmas might be in individual theories, such as the theory of equality, where I interpret function symbols, and the theory of linear arithmetic. This was developed in the original SMTCoq. What we did was to add a couple more theories, bit vectors and functional arrays. That is, we added in SMTCoq support for these two theories, which means basically implementing suitable data types in Coq and proving the correctness of a number of properties that are needed to define the small checkers. Okay? So we created a bit vector Coq libraries that mirrors the bit vector theory as used in SMT solvers, and similarly for functional arrays. Then the idea, the nice thing about the design of the system is that the architecture is such that if you want to extend the system to more theories or more kinds of derivations, so in particular to more external systems, you just have to add more rules and more small checkers. Okay. So everything else that does not need to be touched, so it's quite nice. So I'm to give credit to the original developers. In fact, we found it easy to add our extensions exactly thanks to that. Now, just to get a general idea of how that worked, so the overall checker is as this signature. So it's a function that takes a formula, a certificate, and returns a Boolean value in Coq. Now, the formula is an embedding in Coq of SMT formulas, and the certificate is a term that is in SMTCoq certificate format. I'll give you an example in a moment. And the embedding is a deep embedding because we define an interpretation of SMTCoq from formulas to Boolean values, which is essentially, it is more or less the way you would expect. So the soundness lemma says that if you, for any formula F and certificate C, if the checker returns true on that formula certificate, then the formula is valid. It is the interpretation of that formula is true.
So this is a pure Coq theorem.
I don't know what you mean by pure.
But it's only about something that's been described.
This is entirely in Coq.
Exactly.
That's the way you're asking. So formula is a type that reflects the SMT formulas.
Okay.
Is type formula and also the type certificate parameterized somehow by the kind of theories you're able to do?
They're not parameterized, but the formula is essentially an inductive type. So if you want to add more theories, you need to extend that type.
Okay.
And you must have written your small checkers in a smart way so that you have a catch-all case that it catches all the things that a small checker doesn't actually deal with. Okay. Usual issues when you deal with.
There is a style guide.
Sorry?
There is a style guide.
There should be, if there isn't one, there should be, because you really want to follow the style too. So we're not doing anything fancier than that to enforce modularity. Okay. Now, of course, you get the soundness by actually now proving the soundness of all the small checkers. I don't have time to give you details about that. So as a recap, what do we have right now? So we have this list of theories that are currently supported in SMTCoq and these solvers. ZChaff is actually a set solver. This was done originally, but by and large, you don't need to use it anymore because the SMT solvers can do set as well, just as efficiently. The native SMT solver, so to speak, was veriT, which has been developed at Riyadh as well. We added CVC4. The supported theories are the ones that you have. Now, what is the scope of SMTCoq right now? What kind of goals can you send to that? Well, technically, you can send Boolean goals. That is a formula that you can't represent as a Boolean term, so effectively a quantifier-free formula, but as a goal, you're quantifying over all the symbols in there, so a universal formula. Okay? In classical first-order logic. What we did, however, also to extend this, through tactics, so that you can actually send a prop that isn't the same fragment. That is, you can send a universal formula, a universal prop that, when translated with our translator, produces quantifier-free Boolean formula. Now, here I'll focus on our addition, in particular, fixed with bit vectors and functional arrays, because this is where most of our work went. This was necessary to add support for CVC4. So CVC4, for those who don't know it, is a widely used award-winning SMT solver, showing off a bit, developed here jointly at Iowa and Stanford. It supports a lot of theories listed there, plus more. It's a very large system. And now we are about 250,000 lines of code, C++ code. So you don't want to trust it. And it's completely unrealistic to try to prove that it is correct. So that means that we instrumented it to be proof producing for skeptical users in particular for this integration. So it produces detailed proofs in so-called LFSC format. And LFSC is an extension of the logical framework, Edinburgh logical framework, that was developed by Aaron Stump-Dye and improved by myself. It's based on LF, and so it's basically a meta logic. So you're able to define in it a large number of proof systems, in particular the kind of proof systems that we use in SMT and specifically in CVC4. So it comes with its own checker that is a checker generator really. You feed it the proof system as a LF signature, and then it'll produce automatically a very efficient generator for proofs in that signature. The twist here that we've added subcondition, which are computational checks that you can add to a rule that make generating proofs more practical. Instead of having humongous proofs, you can get a more compact one by sacrificing a little bit of declarativity in there. It's fairly powerful.
8 minutes.
Sorry?
8 minutes.
Yes. It's fairly powerful, and we don't need all that power, but in particular, we can represent SMTCoq proof certificates.
What would be a concrete example of a side
Suppose you have the simplest kind I can give you the resolution rule. So the resolution rule says, I have these two resolvents, or these two clauses C1 and C2 and produce resolvent C. And then the second condition says, well, C is generated by using literal P in the first clause and literal not P in the second clause. And in fact, it's the union of all the remaining literals. So this is checked in the second condition. So how would that work? So you have this coq bowl. This is prop, but it's over Booleans really. Just as a simple example. So we have a tactic like called CVC4 persons that will effectively produce this SMT-lib script, send it to CVC4. SMT solvers do proofs by resolution, and so the whole mechanism here is geared towards, by refutation, so all the mechanism is geared towards that. So here we're basically trying to prove that this set of assertions is unsatisfiable, that would correspond to the original goal being valid. This is just flashing you the LFSC proof produced by CVC4. Now, mind you, we do more complex stuff. So, for this small example, we have a bigger proof than we need. But this proof is then converted into the proof that SMTCoq wants. So this is a simpler format that is supported by SMTCoq. Uses a bunch of fixed rules that are enough for the sort of things that need to be done in SMTCoq. This proof is given back to SMTCoq. SMTCoq replace it effectively, and if successful, we'll get as a consequence that the lemma has been proved. The goal has been proved. Okay. Yes?
But there's a pre-processing step, right?
In the
Well, there's
preprocessor
a
we
whole
trust.
processing, whole translation from here to here.
And then
Now that could be buggy.
and that's
right?
not checked.
Well, the worst that can happen is that the proof doesn't go through.
The proof that you obtain will still be checked afterwards.
Yeah,
But
yeah,
then
you check this proof.
I check
Oops,
this
sorry.
proof and I obtain a proof of the pre-processed formula, right?
Mm.
And then
No, this isn't the pre-processed formula. This is the formula that we got here, okay? So this formula is the formula that has been generated by the original goal, okay? But the translator here into the formula that is certified. Okay, so this formula corresponds to the original goal.
yes, sure.
Now,
That's
the
a
only
preprocessor.
problem might be
Then-
that this proof, when translated in this proof, that is, when translating from this proof to this proof, you might have errors in the translator. But if this happens, what's going to happen is this proof is not going to go through.
But
And
what's
the
the
generator
preprocessor
first.
in the whole story? I mean, there was on 16 on the previous slide, you had the comment that looks very worrying. In the
Sure.
preprocessor we trust. What does that mean?
Oh, you did?
Yeah, that's the thing that I think is bugging us.
Oh, this is what you're referring to. Okay. we can do some pre-processing of the formula that simplifies it, okay? But I was going to talk about this.
Oh, yeah, sorry. Well, that's what we see hold on line 4. This
Yes,
is also
exactly.
worrying us.
These are good questions. I have now 3 minutes to tell you about them. So, in fact, I guess at this point I won't have a lot of time to give you details of how we did bit vectors and arrays. So let me go over these quickly, and then I'll take your questions. So why we choose these theories? First of all, the motivation is that they're useful to reason about programs. There's a lot of Coq users that want to use Coq for that. It's the bit vectors that allow you to implement machine level integers with various operations. Fully important numbers are built on top of bit vectors. Hardware designs, of course, circuits. And arrays can model actual arrays or model memory and all data structure. So they're quite useful. So the way we implemented bit vectors was as a dependent type because they're fixed size bit vectors. So the size of the bit vector is a parameter here. But internally we had to give a concrete implementation, and that is given in terms of a record that contains a list of bits corresponding to the bits in the bit vector explicitly, and then a proof obligation that this list has size n. So now that means all the operations that we do have to make sure that all the constraints on the sizes are respected. And then when we create the actual external type bit vectors, then there was big, large effort in proving that everything checks. Okay. I will skip the issue of bit blasting just to tell you that because bit vectors are typically implemented in SMT solvers by blasting them to their bits and then using in a Boolean sense, you're going to get proofs that look like that. So you need to have rules that relate bit vectors at the abstract level to their bit blasting implementation. So we had to add all of these rules and prove them all correct. For instance, this example here, this rule says if x is represented, the bit blasted version of x is x1 to xn, and similarly for y, then they're equal. You can derive that they're equal if and only if all the corresponding elements are equivalent as Booleans. Well, again, we defined all the small checkers that we had to check all of these rules and prove their soundness. We support basically the whole theory of bit vectors in SMT-lib, which is really large except for the division operator. We just not have time to do this until now. We also did arrays. And now arrays were quite a challenge because arrays have extensionality. The theory of arrays in SMT has extensionality, meaning that two arrays that have exactly the same elements at corresponding positions are supposed to be equal. And now we needed a decidable equality in Coq to be able to support that. And so we're implementing arrays as basically cheating a little bit. Arrays in SMT-lib, in SMT, are essentially maps from an index domain to a value domain. That's all they are. But if you limit yourself to the quantifier-free fragments, you can, without loss of generality, consider only models where you have arrays as almost constant functions. They're everywhere equal to some value except for finitely many places. They're equal to other values. And so we implemented them as finite maps exactly this way. So they are finite maps. There is a default value that is some distinguished value in the type of the results of the array. And also the actual concrete representation of arrays imposes constraints on what they look like so that we have a normal form. All the mapping pairs have to be ordered. There must be no repetitions, no mappings to the default value. So that now two arrays are equal if and only if they're structurally equal. Okay, so I'm just giving you some details to see that there was considerable work in making this work efficiently into Coq and getting this sort of things. Okay, so this allowed us to basically support reasoning over the arrays that is based on these three rules. Don't have time to do a demo at this
How
point.
much time do you need?
I'll be able to do a demo offline. Okay, for people who are interested. Now, I want to address that question because it's very important. I think it's a very cool feature of SMTCoq. Right now, because of pre-processing, CBC4 will produce incomplete proofs with those holes, because the pre-processing steps are not proof producing. That's what in the preprocessor we trust means. So, but what does that mean? That we can't produce a full proof. We literally produce proof with holes, but we modified SMTCoq to recognize that. So when it gets back an incomplete proof, effectively what we'll do is generate subgoals for those holes. So in fact, this makes the system interactive. That is, if you get a full proof, then the system will say, okay. But then if there are these holes in it, then the system will say, well, this will work, provided that you can prove these other steps or these other lemmas that we are not able to provide a proof for. Now, in this case, we know that the lemmas hold, we just don't have a certificate. So what you can do is either use the other solver, veriT, to do this. You might be able to fill in proofs with those holes, or use some of the rules in your theories as rewrite rules to simplify. So this is very nice, I think, because it's not a one-off, it's not a black and white interaction with the solver. Either it proves it or it doesn't. Effectively, it's able to produce, or can be instrumented to produce conditional proofs, okay? Which I think is really nice. Okay, so the conclusion is already here. Modular integration, fairly efficient because of the reflective checker. Most of the stuff is computational. Supports multiple solvers for various useful theories. In particular, we think we have the first certified checker for bit vectors and arrays, and provides automation and semi-automation the way I just described through Coq tactics. When we want to do improved support for protocols, right now the tech is kind of shaky. They work in most cases, but not all of them. And also provide other realization for bit vectors than what we did, because this might allow us to make other users happier. For instance, in ComCert or in Bedrock work, they use their own version of bit vectors. We would like to support goals with quantifier alternations so that we can capitalize on the fact that now SMT solvers can prove not just quantify-free goals, but also quantified ones. And we want to increase the support of conditional proofs the way I just described. Okay, thanks for your patience. Once more, if you want to see the system, I'll be happy to give you
We'll get a demo from the mezzanine area sometime.
Yeah.
Okay. Well done.